Well, you see, there's a question that's been lingering in my mind, and perhaps in yours too. What if the world you touch, the one you trust with every breath, is only a thin curtain over something far stranger, far more delicate, and far more beautiful than we ever imagined? I suppose that's the thing about the quantum world. It sits beneath our everyday lives like a quiet pulse, a hidden rhythm shaping matter, shaping light, shaping time itself. And yet, most of us never stop to wonder what truly happens in that tiny realm where certainty dissolves and possibility blooms. Imagine holding a grain of sand. Inside it, countless particles dance in ways that defy our intuition. They flicker between states, exist in many possibilities at once, and only choose a path when we dare to look. Perhaps that's why the quantum world feels so intimate, almost personal. It reminds us that reality isn't a rigid structure but a conversation between what is and what could be. In a way, it whispers that the universe is not merely observed but co-created with us. And that thought, well, it's both humbling and strangely comforting. As we drift through these ideas together tonight, just you and me, I want you to let your mind loosen a little, like fabric in warm water. Let curiosity guide you. Let the strangeness feel familiar. Because in this quiet corner of 2025, the mysteries of the quantum realm are no longer distant theories. They ripple through every beam of light, every electron in your body, every heartbeat. And the deeper we look, the more the universe seems to lean in and look back. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, you see, when we step gently into the first layers of the quantum world, it feels a little like walking into a room where the furniture keeps rearranging itself the moment you blink. And yet, beneath that strangeness, there is a quiet logic, a rhythm of existence that has been guiding our universe from the very beginning. I suppose the best place to start is with energy itself, because in the quantum realm, energy does not flow smoothly like water in a stream. It arrives in packets, tiny bundles that appear and disappear in precise steps. It is as if the universe speaks in syllables rather than long, flowing sentences. And that simple shift in the way nature behaves is perhaps one of the great turning points in human understanding. It was the first whisper that reality is not as continuous as it seems, that beneath the surfaces we know lies a world built from discrete notes rather than unbroken melodies. And then there is light. You know, we tend to think of light as something simple, something we switch on and forget. But the closer we look, the more light behaves like a mischievous storyteller. Sometimes it spreads out like a wave, graceful and soft. Sometimes it snaps into being as a particle, a single point delivering energy in a moment of certainty. The astonishing truth is that it is both, not in the sense of choosing one and abandoning the other, but genuinely both at once, depending on how we touch it, how we interact with it, how we ask our questions. It is almost as if light adjusts its personality to the nature of our curiosity. And perhaps that is a reminder that the universe is not rigid, but responsive in ways we are still struggling to comprehend. Electrons, too, carry this dual nature. We imagine them as tiny spheres orbiting a nucleus like planets around a star. But that picture, well, it falls apart almost immediately. Electrons are not little marbles. They spread like waves, and the only way to describe them with any honesty is through what physicists call a wave function, a mathematical whisper telling us where an electron might be rather than where it is. And that is the thing about the quantum world. It does not deal in certainties, only probabilities. When we describe an electron, we describe all the possibilities of its existence at once. It is a cloud of potential, a presence smeared over space until we decide to measure it. And, that act of measurement, it changes everything. The moment we observe, the moment we interact, the wave function collapses. The electron chooses a position. It commits to a single story. Before that, it is countless stories woven together. After that, It is only one. You might think of it like this. Reality in the quantum sense is not a painting, but a menu. The painting appears only when we look. It is a strange thought, perhaps even unsettling, yet it is supported again and again by experiments that push our understanding of nature to its limits. The quantum world challenges our instincts. It asks us to give up the comforting notion that nature exists in a definite state, whether or not we look. Instead, we are told that potentials swirl beneath everything, waiting for our touch to solidify into facts. It is not that nature hides the truth from us. It is that truth itself is a fluid concept until an interaction pins it down. And that leads us to a curious question. What is a measurement? In our everyday lives, we imagine it as simply observing, seeing, noting something. But in the quantum world, measurement is not merely watching, it is participating. Every measurement is an interaction, a disturbance, an entanglement of observer and object. The electron cannot reveal its position without being touched in some way. The photon cannot show its path without being interrupted. So perhaps, in a way, measurement is the universe's way of allowing us to join the story, to leave a mark on the unfolding of reality. Perhaps the most remarkable thing about this is what it reveals about our own assumptions. In the world we navigate each day, we tend to take for granted that objects have definite locations and speeds. But in the quantum world, the idea of knowing both precisely is impossible. Not because our instruments are crude or our methods flawed, but because the universe itself places that limit. The electron cannot have both a perfectly known position and a perfectly known momentum. The more we squeeze certainty from one, the more uncertainty blooms in the other. It is a built-in feature of reality, as fundamental as gravity. And there is something deeply philosophical about that. It reminds us that control, certainty, and precision are not always virtues that nature supports. The universe is not a machine following rigid pathways. It is more like a field of possibilities unfolding moment by moment. And in the calm of night, when we look up and wonder who we are in this vast cosmos, the quantum world quietly suggests that not everything needs to be pinned down. Some things are meant to remain uncertain, free, open. If we think of time as a landscape, as I often do, then perhaps quantum behavior is like the mist that rolls across it. The closer you walk toward it, the more it shifts. The harder you try to grasp it, the more it slips through your fingers. But step back, take it in gently, and the mist reveals patterns, movements, and a strange, ghostly coherence. This is the foundation upon which modern physics stands. Every electron in your body behaves this way. Every photon that reaches your eyes carries this dual nature. The entire universe is built from these quantum rules, yet we rarely pause to notice how astonishing that is. We live in a world shaped by uncertainty, by discrete packets of energy, by particles that are also waves, by realities that do not exist until they are observed. And in 2025, with all our technology, with all our knowledge, we are only beginning to understand what that truly means. Perhaps the most beautiful realization here is that quantum mechanics does not merely describe the small. It describes the very foundation of everything. It is the quiet machinery beneath matter, beneath life, beneath the stars. And as we explore this first layer together, we begin to see that these ideas are not isolated facts. They are pieces of a deeper tapestry, threads that connect to principles even stranger, even more wondrous. And so, as we move forward, as we peel back another layer of this intricate universe, one question naturally emerges. If uncertainty and probability are built into the fabric of reality, then what does that say about the limits of what we can know? What does it reveal about the very nature of measurement, of knowledge, of existence itself? Well, that question leads us, gently and irresistibly, into the next mystery waiting for us. The mystery of how uncertainty becomes a law of nature, one that defines the boundaries of what can be known. And that is where our journey will take us next, as we step softly into the realm of the principle that has reshaped our understanding of reality, more profoundly than almost anything else. Let us walk toward it together. Well, you see, once we've taken that first step into the quantum landscape, where certainty melts into probability and particles linger as clouds of possibility, we find ourselves standing before one of the most unsettling and beautiful truths ever uncovered. It arrives quietly, almost politely, yet it reshapes everything. And that truth is woven into what we call the uncertainty principle. Not uncertainty born of human error or clumsy instruments, but uncertainty as a fundamental property of nature itself. It is as if the universe is whispering that some things are not meant to be pinned down, that precision comes with a price, that knowledge itself has limits built into the very fabric of reality. As we move forward from where we left off, you might imagine that if we simply built a better microscope, a sharper device, a more sensitive detector, we could one day track the position and speed of an electron with perfect clarity. But the universe, gently denies this. The closer we try to press down on an electron's location, the more its momentum writhes and stretches beyond our grasp. It's almost like trying to hold a bubble in your hands. Tighten your grip on one side, and the other side squirms and escapes. The two quantities are entangled in a dance of natural trade-off, where knowing one steals certainty from the other. And that's the thing. This uncertainty does not come from technical limitation. It is not an engineering problem or a challenge waiting for a technological breakthrough in some distant laboratory in 2025. It is the way reality works. It is baked into the geometry of the quantum world. The electron is not a solid bead traveling along a clean orbit in space. In fact, the very idea of a perfect orbit evaporates the moment we zoom into the quantum scale. There are no neat pathways like planets curving around a sun. The electron does not trace a line. It hovers in a fuzzy probability cloud, shifting not because we cannot see it clearly, but because its nature refuses to be reduced to a single trajectory. And once you let go of that old image of electrons circling like tiny moons, the quantum world becomes a little easier to accept, though still endlessly strange. The quantum realm simply does not permit the classical picture of motion we grew up with. If you ask an electron, "Which path are you taking?" the universe seems to reply, "Path? What path?" The question itself no longer makes sense. The electron behaves more like a ripple of possibility than a particle marching along a deterministic route. This is where the uncertainty principle becomes more than a scientific statement. It becomes a philosophical doorway. It tells us that at the deepest level, the universe is not a clockwork machine grinding predictably through time. It is a landscape of vibrations and fluctuations. Even what we would normally call emptiness, the vacuum, is not empty at all. It seethes with energy, trembling with the smallest possible vibrations of the fields that fill all of space. If you could somehow freeze time, still your breath, and stare into the very heart of nothingness, you would see flickers of energy rising and falling, particles appearing and vanishing like sparks in the darkness. And perhaps that is where uncertainty becomes its most poetic. Even when nothing is present, something stirs. The quantum vacuum is alive with motion. Not motion like the sway of trees or the orbit of stars, but motion in the sense that fields cannot sit perfectly still. They jitter, they shimmer, they pulse. These tiny fluctuations, brief beyond imagination, give rise to what physicists call virtual particles. They are not particles in the everyday sense. They flash into existence and vanish almost immediately, borrowing energy from the vacuum under the condition that they repay it in a time so short that the universe merely shrugs and allows it. You might think of it like borrowing a cup of sugar from a neighbor, but returning it before they even realize it was gone. The universe permits this kind of borrowing as long as it happens quickly enough. And the faster the borrowing, the more energy can be taken. Time and energy, like position and momentum, are bound by a similar uncertainty. The shorter the time allowed, the greater the energy that can burst into being. These ephemeral particles teem throughout the vacuum at every moment, influencing everything from the structure of atoms to the expansion of the cosmos. And I suppose if you let your mind wander a little, you might begin to see how profound this is. Even the emptiest parts of space, those vast stretches between stars, galaxies, and clusters, are not truly empty. They are a storm of fleeting events, a restless ocean of virtual flickers. The vacuum is more like a living fabric than a blank void, and this realization hints at something even deeper. If every point in space vibrates with quantum energy, then the universe is fundamentally dynamic, restless, alive at its core. The uncertainty of the vacuum stretches far beyond philosophical curiosity. It shapes reality in subtle yet powerful ways. These virtual particles tug on the energy of space, influence the behavior of electrons, and contribute to the structure of matter. And even though they vanish quickly, their presence leaves measurable fingerprints. They change how atoms behave. They shift the energy levels of electrons. They even play a role in the structure of the vacuum that drives the expansion of the universe itself. It is strange, perhaps even a little humbling, to realize that the universe's restlessness underlies our existence. The atoms in your body are stable only because virtual particles dance around the nucleus, influencing the forces that hold everything together. Life, in a way, is built on fluctuations so brief they almost escape the definition of existence. And all of this, every trembling of the vacuum, every uncertainty in momentum, every refusal of electrons to follow clean orbits, flows directly from that one principle that Heisenberg placed before us. A principle not of ignorance, but of nature's own limits. The universe is not hiding information. It simply does not possess the definite values we demand, until interactions force them into being. Well, perhaps that is what I find most beautiful about the uncertainty principle. It invites us to see the universe not as a perfect blueprint, but as a living process, a place where possibilities are always unfolding, where potential is always simmering beneath the surface. It whispers that there will always be mystery, always be room for wonder, always be horizons of understanding we may approach, but never fully claim. And in an age like 2025, where we often feel pressured to know everything, to measure everything, to predict everything, the quantum world quietly reminds us that uncertainty is not a flaw. It is a feature, a gift. You might wonder then, with particles refusing to take clear paths and reality itself jittering in the vacuum, what happens when particles exist in more than one state at once? If uncertainty can blur a particle's position and momentum, could it go further, blending multiple realities into a single shimmering possibility? And that, is the doorway to another marvel of the quantum world, perhaps even stranger than uncertainty itself. A place where particles do not simply fluctuate, but coexist in overlapping states, a phenomenon that stretches our imagination even farther. Let us drift gently into that next mystery together. Well, you see, once we've stepped through the veil of uncertainty, where the universe whispers that not everything needs to be known at once, we find ourselves facing a phenomenon even more elusive, even more daring in its implications. It is as if nature, having already shown us that certainty is limited, now leans closer and says, and yet, reality can be more than one thing at the same time. And that idea, gentle and shocking all at once, is what brings us into the strange, shimmering territory of superposition. Perhaps the simplest way to feel the depth of this is to imagine standing at a crossroads. In everyday life, you choose one path and the others fall away behind you. But in the quantum realm, at least before anyone looks, a particle takes all the paths. It explores every option, touches every possibility, and somehow holds them together in a delicate balance. A quantum object is not here or there. It is both. It is not in one state or another. It is a blend, a harmony of potentialities unfolding all at once. And the more you sit with that, the more you realize just how different the quantum world is from the one your intuition grew up in. Take the electron, for instance. We tend to imagine it sitting neatly in one orbit, as if it were a tiny moon around an atomic planet. But in truth, before we measure it, the electron occupies many orbits at once, not metaphorically, but quite literally in the language of quantum mechanics. Its wave function spreads out like a soft, rippling cloud that touches many states simultaneously. The electron is not in one place or one energy level. It coexists in all possibilities that are mathematically allowed. And when you let that thought breathe for a moment, it begins to feel almost like a meditation on choice, on identity, on the fluidity of being itself. This notion of coexistence reaches one of its most famous expressions in the thought experiment involving a cat sealed in a box. Now, I suppose you've heard of it. Schrödinger's cat, a hypothetical creature suspended between life and death, existing in a mathematical superposition of both states until someone opens the box. It sounds absurd, almost playful, as if Schrödinger were joking with us. But the idea behind it is deadly serious. If the quantum laws apply to tiny particles, why should they stop applying as things grow larger? And what does it mean for something to be both alive and not alive at once? Of course, no one believes a real cat would ever rest in such a limbo. But the experiment forces us to confront the slippery boundary between quantum possibility and classical experience. And that's the thing. Superposition is not just a theoretical curiosity. It is one of the pillars holding up the entire quantum structure. The mathematics of quantum mechanics tells us that until you measure a system, it exists in this blend of states, this layered tapestry of potential. The system is not indecisive. It is not confused. It simply is in a way that our classical minds find challenging to express. Reality, at that level, is not singular. It is plural. It is a chorus of possibilities. But the moment you measure it, something astonishing happens. That broad spectrum of potential outcomes collapses into one. The electron picks a location. The atom chooses an energy. The cat, in the metaphorical box, becomes either alive or not. Your act of observing, or interacting, or disturbing forces the universe to settle on a single version of events. And perhaps that is what makes superposition feel so poetic, almost philosophical. It is as if the universe remains open, fluid, generous with its possibilities, until the human act of measurement asks for a decision. You might think of it like an unread book. Before you open it, the story could unfold in countless ways. Heroes might triumph or fall. Journeys might end in joy or sorrow. The narrative could twist into surprises or sink into familiar patterns. All these paths exist in a kind of literary superposition, but once you read the pages, the story chooses one path, and all the others dissolve. The quantum world behaves much the same, except nature herself holds the book's potential stories until a measurement snaps the pages into a single narrative. This strange ability to exist in multiple states at once is not just a philosophical curiosity. It is the very engine behind quantum technologies emerging in our century. Consider the qubit, the basic unit of information in a quantum computer. A classical bit can be either 0 or 1. There is no ambiguity, no softness in between. But a qubit, nurtured delicately in a quantum system, can be both 0 and 1 simultaneously. It can blend those states in countless combinations. And the more qubits you entangle in superposition, the more computational pathways you open. Instead of exploring one route at a time, a quantum computer explores many, balancing them in a shimmering superposition until measurement collapses the final answer into something we can read. And perhaps this is where the wonder deepens. Superposition is not merely a scientific principle. It is a tool for stepping into realms of calculation that classical machines cannot reach. It promises to reshape everything from cryptography to chemistry, from optimization to artificial intelligence. In a world like ours, in this quiet slice of 2025, superposition stands at the heart of a technological revolution that is only beginning to unfold. But beneath the machinery and mathematics lies a more subtle truth. Superposition challenges our understanding of what it means for something to be real. If a particle is in many states at once, but we only ever see one outcome, where do the others go? Were they ever truly there? Were they only mathematical conveniences? Or do they represent genuine layers of reality that simply slip beyond our observational reach? These questions, whispered from the quantum depths, ripple into the heart of philosophy itself. And perhaps the most eerie implication is this: reality, before observation, is not definite. The universe waits for us. It waits for interactions. It waits for moments that crystallize potential into fact. And that waiting, that openness, gives superposition a kind of dreamy softness, a poetic shimmer. Reality is not merely discovered. It is in part created through observation, not because our minds impose structure, but because interaction forces nature to choose. It is worth pausing for a moment here. Imagine a world where coins spin forever in the air until someone looks, where melodies blend all notes at once until a musician strikes a string, where paths through a forest remain undetermined until a traveler steps forward. That is the quantum world, a world in which being is a spectrum, not a point. And yet, as strange as it sounds, this is not chaos. Superposition obeys precise mathematical rules. The way states overlap, interfere, strengthen, cancel, they form patterns elegant and predictable within the quantum framework. If uncertainty is the soft mist lying across the landscape of time, then superposition is the layered valley beneath it, where many rivers run in parallel until one is chosen. Still, even with its beauty and precision, superposition leaves us with deep, lingering questions. If particles can inhabit multiple states at once, can entire worlds do the same? Could there be branches of reality where different outcomes unfold? Could every unchosen possibility still find expression somewhere beyond our reach? These questions inevitably draw us toward yet another layer of the quantum narrative, a place where entanglement and shared states stretch across vast distances, connecting particles in ways that defy classical intuition. But before we wander into that next terrain, let us linger for a moment longer with the imagery of superposition. Imagine the space around you filled with infinite tiny harmonies, each particle humming not one note, but chords of existence, each electron not choosing a home, but drifting across a constellation of possibilities, each atom carrying within it not a single identity, but a multitude quietly waiting for a reason to choose. It is almost a reminder that the universe we inhabit is far richer than the one we see. And in a way, it encourages us to hold our own lives a little more lightly. Perhaps we, too, are not locked into one single version of ourselves. Perhaps we carry within us many possibilities, many paths we have yet to take. And as we drift further into this quantum night, with superposition shimmering behind us, a new question begins to form. If particles can exist in multiple states simultaneously, what happens when two particles become linked? What happens when their fates intertwine so completely that touching one instantly shapes the other, no matter how far apart they are? Well, that quiet question opens the doorway to one of the most haunting and beautiful mysteries of all. Let us step toward it together. Well, you see, once we've drifted through the strange quiet of superposition, where particles hum in many states at once like notes of a chord still waiting to be played, the universe invites us to take another step into an even deeper mystery. And perhaps this is where things become almost dreamlike, because what comes next challenges not only our understanding of physics, but our sense of separation, of space, of distance, of what it means for one thing to be distinct from another. It is here, in this soft and uncanny twilight of quantum behavior, that we encounter entanglement. And the more time you spend with it, the more it begins to feel like a kind of cosmic intimacy written into the fabric of nature. Imagine this: two particles, born together or pushed into interaction for a brief moment, begin to share a state so profoundly that their identities intertwine. They become, in a sense, a single system. Even if you send one particle to the far side of the galaxy and keep the other beside you, their connection remains. Change one, and the other responds instantly. No signal passes between them in any ordinary sense. No messenger travels across the void. It is as if the universe refuses to let them drift apart, not truly, not in the ways our intuition expects. Einstein, with all his brilliance and caution, found this deeply troubling. He famously called it spooky action at a distance, as if the universe had decided to play a prank on our most cherished ideas about locality. And perhaps he wasn't wrong to be unsettled. Entanglement breaks open the classical picture. It says that space, that comforting stretch of emptiness we imagine lying between things, does not apply in the way we believe. When two quantum objects are entangled, distance loses its meaning. They are bound by something deeper than space. You might imagine two dancers who begin the evening on the same stage, their movements perfectly synchronized, and then, by some miracle, they drift apart, one to a distant city, the other to a mountaintop far away. Yet every step they take remains linked, as if choreographed by an invisible thread. They do not communicate. They do not send signals. They simply move as one because they are one, at least in the language of quantum mechanics. What makes this phenomenon even more astonishing is that entanglement has been tested again and again with extraordinary precision. Experiments have confirmed, to a degree that would make even the most skeptical scientist pause in wonder, that entangled particles respond to each other instantly, no matter how far apart they are placed. No delay, no lag. The change is simultaneous, as if the universe itself is shrugging off the limitations of distance. And that's the thing. Information in entanglement does not travel through space because it does not need to. Entangled particles do not hold separate information that needs to be communicated. They share a single quantum state, spread across space like a single breath held between two bodies. So the moment one particle is measured, the shared state collapses, and both particles reveal outcomes that fit together perfectly. Not because one sends a message to the other, but because they were never truly separate to begin with. Perhaps this is what challenges our intuition so deeply. We have grown up believing that objects exist independently, that things here are disconnected from things there. But entanglement dissolves that boundary. It whispers something subtle and profound. Separateness is not fundamental. Unity runs deeper than distance. If you sit with that idea for a moment, it begins to shift something inside you. It becomes more than physics. It becomes philosophical, emotional. The universe, in its quiet quantum undercurrent, suggests that connection is woven into reality at the most fundamental level. And in the soft glow of night, when you think of those bright stars scattered across the sky, it feels strangely comforting to imagine that beneath the vastness lies a web of entanglement, a hidden structure linking everything through patterns of shared existence. But entanglement is not just a poetic notion. It is a working principle, a resource that physicists now manipulate with increasing precision. It forms the backbone of quantum communication, a technology that promises to reshape the world in ways we are only beginning to glimpse. Entangled particles can transmit information with absolute security because any attempt to intercept the signal breaks the entanglement itself. In a world like ours, in this quiet stretch of 2025, entanglement is poised to become the foundation of quantum networks, communication channels that no classical hacker could ever breach. There is something breathtaking about that. A principle once dismissed as impossible, or at least deeply suspicious, has become a tool for building the future. Entanglement is no longer merely a quirk of theory or a philosophical puzzle. It is the heart of quantum technologies that are slowly emerging into the light. And yet, even with its practical uses, entanglement remains one of the purest mysteries in all of physics. How can two particles become one system? How can the collapse of a wave function, happening here, define the state of another particle kilometers away, instantly? How can the universe coordinate such perfect synchrony without signals, without mediation, without time for communication to flow? Well, perhaps the problem is that we keep trying to force the quantum world into the shapes of our classical expectations. Perhaps entanglement feels spooky only because we insist on thinking of particles as separate objects living in separate locations. But the quantum world may not be organized that way. It may be more holistic, more relational, a place where distance is secondary to the deeper patterns of correlation that define reality. To understand this intuitively, You might consider the idea that what we call space is not the fundamental stage upon which physics plays out. Maybe space is a construct, an emergent property of deeper quantum relationships. Entanglement could be the scaffolding from which space itself arises. Some physicists are exploring precisely this idea, that geometry, distance, even the shape of the universe could emerge from networks of entangled particles. If that is true, then entanglement is not merely a phenomenon within space. It is the foundation upon which space is built, and perhaps that is the most astonishing idea of all. The universe we see, the planets, the stars, the galaxies drifting through the cosmic ocean, may be woven from threads of connection so subtle we only discovered them a century ago. Entanglement, in this sense, is not just a feature of the quantum world, it is the architecture of reality. But even if we set aside those deeper possibilities, entanglement still compels us to rethink everything. The classical world of separate objects with independent properties crumbles under its weight. In the quantum world, properties emerge only when we measure them, and entangled particles reveal those properties together. They are coordinated, harmonized, bound not by forces but by a shared history, a shared state, a shared mathematical description. And the more you consider it, the more it feels like a kind of cosmic togetherness, a reminder that at the deepest levels the universe is not fragmented, it is interconnected, it is whole. But entanglement also leaves us with a lingering question. If particles can be tied together in ways that defy distance, if their shared reality collapses into clarity the moment we observe one of them, what does that say about the nature of the particles themselves? Are they truly particles? Are they waves? Are they something else entirely? Well, that gentle question begins to lead us toward the next shimmering truth in our journey. Because to understand what entanglement truly means, we must step back and reconsider what particles even are. And that road brings us to a place where the line between particles and waves dissolves, a place where every object in the universe dances between forms depending on how we choose to look. Let us wander there together. Well, you see, after wandering through the strange connectedness of entanglement, where separation softens and distance seems to lose its authority, it becomes natural to ask a deeper question. If two particles can share a single state across vast stretches of space, then perhaps the very idea of what a particle is needs to be re-examined. And as we lean closer, letting our curiosity guide us, the universe reveals something wonderfully perplexing. That particles are not merely particles. They are also waves, not metaphorically, not symbolically, but literally in the language of quantum mechanics. Their identity shifts with the way we touch them, the way we ask our questions, the way we choose to look. And that is where our journey brings us next. Imagine holding a small pebble in your hand. It feels solid, definite, reassuring. If you throw it, it traces a clean arc through the air. If you drop it, it falls. It behaves like an object should. Now imagine shrinking that pebble down, smaller and smaller, until it becomes an electron. That is where intuition breaks. The electron is not confined to a trajectory like the pebble. Instead, it spreads out. It behaves like a wave, extending across space, interfering with itself, carrying a wavelength tied to its momentum. Every particle, no matter how small or large, comes with such a wavelength. Even you, sitting quietly wherever you are in this moment, have a wave associated with your mass and motion. It is unimaginably tiny, far beyond any chance of detection, but it is there. A small reminder that wave nature runs through all matter, from the humblest photon to the atoms that make up your bones. Perhaps the most striking demonstration of this comes from the double-slit experiment, a piece of scientific theater so elegant that it reveals the wave nature of matter with almost painful clarity. When electrons pass through two openings, they do not simply go through one or the other. Instead, they behave like waves, spreading, overlapping, and forming an interference pattern on the other side. But here's the thing. The electrons pass through one at a time. They are not bumping into their neighbors. They are not coordinating. Each electron interferes with itself, as if it travels through both slits simultaneously, as if it is both a particle and a wave entwined in a single existence. And that's the thing. If you try to watch which slit the electron goes through, the interference disappears. The electron chooses a path. The wave collapses into particle-like behavior. The very act of measurement reshapes the story. It's as if nature asks us, gently but firmly, what question are you asking? If you ask about position, the electron becomes a particle. If you ask about behavior across space, it becomes a wave. Reality shifts according to the nature of our curiosity. Light, too, wears this dual identity. Shine a beam through a glass of water, and you will see it bend like a wave. Let it diffract through a narrow opening, and it spreads out like ripples in a pond. Yet when a photon strikes a metal plate or triggers a detector, it arrives as a particle, a discrete bundle of energy that delivers a tiny push or releases an electron from an atom. Light is not indecisive. It is complete. The wave description and the particle description are simply two ways of understanding a deeper structure that transcends both metaphors. And perhaps there is something beautifully humbling in that. We often imagine the world as composed of things, solid objects, particles, building blocks. But the quantum world suggests that what we call matter is more like patterns of vibration, oscillations in fields that stretch across space. The particle picture emerges only when we measure, when the wave function collapses, when the universe answers a specific question with a specific outcome. But beneath that, matter is rhythm, movement, possibility. Consider again the idea of an interference pattern. When electrons or photons behave like waves, they produce bright and dark fringes in a pattern of astonishing regularity. These fringes are not disturbances created by collisions. They are signatures of superposed waves overlapping, amplifying, and canceling. And as strange as it sounds, every particle carries this potential. Even atoms, full of electrons and protons and neutrons, show wave-like interference when cooled and slowed. Even molecules, large ones containing dozens or hundreds of atoms, have been shown to behave like waves. The bigger the object, the smaller the wavelength, but the principle is universal. The universe does not distinguish between particle and wave. It simply offers a dual description for a deeper, more mysterious reality. And this dual nature reshapes our understanding of motion itself. Classical physics tells us that objects move along paths, but quantum physics whispers that paths do not exist until we measure them. Between measurements, the object spreads out, blurring into a wave that touches many places at once. It is only when we ask for a position, a location, a path, a point in space, that the wave collapses into something particle-like. In a sense, the world waits for our questions before it decides on its answers. Perhaps this is why the quantum world feels so alive, so dynamic. It refuses to be boxed into a single mode of being. It refuses to settle until forced. And even then, its particle-like behavior hides the wave-like story beneath it. Each particle is a wave. Each wave can appear as a particle. And the universe moves effortlessly between these descriptions depending on how we choose to look. One of the most fascinating consequences of this duality is how it shapes our understanding of forces and interactions. When a photon bends around a star or passes near a planet, we can describe this bending either as a particle moving through curved spacetime or as a wave following the geometry of a gravitational field. Both descriptions work. Both are true. It is as if nature offers us multiple windows into the same underlying reality, each revealing a different facet of the cosmic mosaic. And think of how this affects the way we see ourselves. If every particle in your body carries wave nature, then you are not merely a collection of fixed points. You are a symphony of vibrations, a tapestry woven from oscillations in quantum fields. You are stable only because these waves settle into patterns that repeat with extraordinary reliability. Matter is not a thing. It is a process, a song frozen in time, held together by the rhythm of quantum waves. This realization also nudges us toward a subtler thought. That identity in the quantum realm is not as strict as we imagine. If particles are waves, and waves can overlap and interfere, then what does it mean to say that one particle is distinct from another? Perhaps the universe does not carve things neatly into boxes. Perhaps separateness is merely a convenient illusion for beings who live at human scales. Beneath that scale, the boundaries blur. Yet even as wave nature reveals breathtaking unity, particle nature grounds the world in the solidity we depend on. When a photon hits your eye, when an electron jumps between energy levels, when an atom absorbs a quantum of light, the particle picture becomes necessary. These are events, discrete, sudden, specific. It is in these moments that the universe resolves itself into a definite act, like a wave cresting into a solid drop before dissolving back into the ocean of possibility. And I suppose that is why this dual description feels so profound. It mirrors the tension inside each of us. We too move between states. We are fluid in potential and yet fixed in the choices we make. We are waves of possibility constrained into moments of reality. The quantum world does not merely describe matter. It reflects the structure of existence itself. But as we dwell on this dance between particle and wave, another question begins to rise. If particles reveal themselves differently depending on how we observe them, then what role do we, as observers, truly play? Are we merely watching the universe unfold, or are we part of the process that shapes it? Well, that gentle question opens the doorway to the next mystery awaiting us. A realm where observation is not passive, where measurement reshapes reality, where the viewer becomes inseparable from the viewed. Let us step softly toward that unfolding truth together. Well, you see, once we've wandered through that shimmering borderland where particles behave like waves and waves collapse into particles the moment we ask them to, it becomes impossible not to wonder about the nature of the asking itself. We've seen how electrons can spread through space like mist until we try to catch them, and how photons can act as ripples or sparks depending on our curiosity. And perhaps you've started to sense, as I have, that the act of observation is not a passive gesture. It is a disturbance, a participation, a kind of conversation with the universe. And that brings us gently into one of the most disorienting and strangely intimate truths in quantum physics. The observer matters. Imagine standing before a still lake. When you look into the water, you see a reflection of yourself, unmoving, serene. But the moment you reach out and touch the surface, the reflection shatters into ripples. That is what observing a quantum system is like. We cannot simply gaze at it. The very act of observation becomes an interaction, a ripple cast into the fabric of the quantum world. And unlike the calm of classical physics, the ripple matters. It changes what we see. It changes what is. The wave function. That strange mathematical whisper that encodes all possible states of a particle hovers in a superposition of potentialities until measured. But measurement is not just reading. It is a physical process. It is a collision, an exchange, a moment where the observer and the observed meet and influence one another. The wave function collapses, not because we look, but because our act of looking involves touching, disturbing, coupling to the system. Perhaps this is why quantum mechanics feels so alive, because it refuses to treat us as external witnesses. It pulls us into the story. And that's the thing. The results we obtain depend on how we measure. If we choose one setup, reality folds itself into one outcome. If we choose another, the universe reveals a different face. The quantum world does not offer a single objective truth independent of the questions we ask. Instead, it offers conditional truths shaped by measurement. The world does not simply exist in a definite state waiting to be revealed. It crystallizes into form through interaction. This is where the idea of objective, observer-independent reality begins to tremble. In classical physics, the world is presumed to have definite properties whether or not we observe them. The moon is there, even if no one looks. The apple falls, even if no one sees. But quantum physics whispers something different. It suggests that certain properties, like the momentum of an electron or the precise path of a photon, do not exist in definite form until measured. They exist only as probabilities, as possibilities, as shapes of potential. The act of observation does not merely uncover a pre-existing state, it helps define it. You might think of reality as wet cement. When left alone, it holds a vague shape, capable of many forms. But when touched, carefully or clumsily, it sets, solidifies, becomes one specific outcome. And once set, that outcome becomes part of the reality we know, part of the world we inhabit. But it could have set differently, had we touched it differently. This raises a quiet but profound question. What does it mean to observe? We tend to think of observation as using our eyes, our senses, our instruments. But in quantum physics, observation means something more subtle. It means interaction. Any coupling of systems, any exchange of energy, any scattering of photons, any entanglement with a detector constitutes a measurement. Even when no human is present, even when no consciousness is involved, quantum systems collapse into definite states because they interact with their environment. A photon striking a molecule, an electron bumping into a detector screen, an atom colliding with another atom, these are all observations in the quantum sense. The universe is full of them. Nature is constantly measuring itself, constantly collapsing wave functions into new realities. We are not the only observers. We are simply one part of the web of interactions that define the world. Yet, even knowing this, something still feels personal about it, doesn't it? There is an intimacy in the idea that reality is shaped through interaction. It means the universe is not indifferent. It responds. It participates. It shifts when touched. And perhaps, in a quiet way, so do we. Consider this. Whenever you make a measurement, the device you're using becomes part of the quantum system. The detector, the lens, the apparatus, all of it merges with the particle under study. There is no clean line separating observer from observed. The measurement process is a merging, a kind of entanglement, a blurring of boundaries. Once the measurement is complete, the system and the measuring device share a history. They carry the memory of the interaction. This, in turn, reveals something even deeper. The outcome of a quantum experiment depends not only on what you measure, but on how you measure it. Change the setup, and you change the answers the universe provides. Reality, at least in the quantum sense, is not a fixed landscape, but a responsive one. It bends, shifts, and crystallizes based on the nature of the questions posed. And when you let that sink in, it becomes difficult to maintain the old distinction between the world out there and the mind in here. The boundary begins to soften. We are part of the system we study. Our curiosity has weight. Our questions sculpt outcomes. It does not mean we create reality from thoughts alone, but it does suggest that reality is shaped through interaction, and that observers, human or otherwise, are woven into the fabric of physical law. Quantum mechanics reminds us that the universe is not a silent, static sculpture. It is a conversation, a dialogue between systems, a dynamic interplay of measurement and response. Every observation is an exchange, like two dancers meeting briefly before drifting apart again. But perhaps the most astonishing part of all is that each measurement creates a new reality, a new branch of possibility that grows out of the collapse of the wave function. Every time a system settles into one state, it leaves behind a vast space of unrealized possibilities. Those possibilities do not disappear lightly. They linger, whispering of paths not taken, outcomes not chosen. And for decades, physicists have debated what becomes of them. Do they simply vanish? Does the universe prune away the unchosen branches of potential? Or, perhaps more strangely, do those possibilities unfold in worlds parallel to ours, each carrying its own version of events, its own history, its own flow of time? Well, that gentle question, rising naturally out of the role of the observer, guides us toward the next great mystery in our journey. a mystery in which measurement does not eliminate possibilities but gives birth to them, a place where every quantum decision branches reality into countless threads. Let us drift into that strange, expanding horizon together. Well, you see, once we've lingered long enough in that strange, trembling space where observation shapes reality, another question begins to rise, quietly at first, like a ripple beneath the surface. If each measurement collapses a wave of possibilities into one outcome, then what happens to all the other outcomes that could have unfolded? Do they simply vanish into nothingness, like a dream dissolving at dawn? Or could they, perhaps, continue somewhere else, in some hidden corridor of existence? And, this is where the universe begins to feel almost story-like, as if physics itself is offering us a myth of branching paths. A myth that many scientists, with surprising seriousness, have taken to heart. It leads us gently into one of the boldest ideas ever imagined, the possibility that every quantum choice creates a new world. Imagine for a moment that each time a particle collapses into one measured state, reality itself splits. One version of events unfolds here, while another unfolds elsewhere. Not elsewhere in space, but elsewhere in possibility. It is as if the universe, unable to discard potential, allows every outcome to bloom into its own branch. This is the essence of what some call the many worlds interpretation. There is no collapse in this picture, no pruning of possibility. Instead, the universe unfolds like a vast cosmic tree, its branches diverging with every quantum event, every interaction, every moment of choice. Perhaps it sounds extravagant, even excessive, to think that each measurement creates another world, another version of you, another history running parallel to the one you know. And yet, from the perspective of quantum mathematics, superposition never truly ends. The wave function does not collapse. It merely becomes entangled with the observer, splitting the world into branches where each possible outcome is realized. Reality becomes layered, multifaceted, like a prism scattering white light into infinite colors. You may wonder then how these branches differ. Are they thin, ghost-like shadows of our own world? Are they as solid, as real as the world you feel beneath your feet? According to the many worlds view, each branch is fully real, each as vibrant as any other. In one world, a particle is measured spin up. In another, it is measured spin down. In one world, a coin flips to heads. In another, tails. And in some unimaginable cascade of branches, every possibility permitted by physical law unfolds with its own integrity. There is no privileged branch, no central storyline, only a vast, ever-growing forest of realities. And that's the thing. In this picture, time itself becomes something more fluid, more branching than linear. Each measurement, each interaction, each quantum event becomes a fork in the river of reality, sending streams in every direction. Time is not a single, narrow channel guiding the universe forward. It is a delta, a fan of branching flows. We experience only one channel because we are part of one branch, but elsewhere, versions of us drift along parallel streams created by quantum events we never felt. It is almost dizzying, isn't it, to imagine that every unchosen possibility might still exist somewhere, that every path you didn't walk, every word you didn't speak, every breath that could have been different might be unfolding in another branch, not because of destiny or desire, but because the mathematics of quantum mechanics refuses to discard anything. The universe in this view is profoundly generous with reality, and yet, even as the idea expands our imagination, it remains anchored in the sober logic of physics. Quantum mechanics predicts that during measurement, the total wave function includes both the system and the observer. If no collapse is introduced, the branching becomes unavoidable. The observer becomes entangled with the outcome. One version of the observer sees one result, another sees the alternative, and the two can no longer communicate. They inhabit different worlds. This leads to an important point. Once the branches diverge, they cannot interfere or exchange information. That is why we never feel the splitting. That is why we do not sense other worlds brushing against ours. In the language of quantum mechanics, the branches decohere. Their histories diverge. Their futures evolve independently. Each branch becomes its own universe, sealed off by the mathematical structure of the wave function. You might imagine these worlds as books on a shelf. Each book contains a complete story, shaped by choices and events, rolling forward through time. But the books do not speak to each other. Their characters never cross the boundaries between pages. And yet all the books exist side by side, sharing a deeper connection through the library that holds them. Some physicists have wondered whether the many worlds picture might help explain the strangeness of quantum behavior. Superposition, entanglement, interference. All of these phenomena become natural if the wave function never collapses. The universe simply continues unfolding in its full mathematical richness, and what we call collapse is merely our experience of landing in one branch. Quantum weirdness becomes classical clarity once we accept that we inhabit only a single slice of a larger whole. But of course, this interpretation raises its own questions. If the universe is constantly branching, why do we experience only one version? Why does consciousness seem tied to a single thread of reality? Perhaps, some argue, consciousness itself is bound to the process of decoherence, slipping into the branch that corresponds to a particular outcome. Or perhaps we are simply one observer among infinite versions, each unaware of the others, each experiencing a world consistent with its own history. And you know, when you sit with that idea for a while, it begins to feel strangely intimate. It suggests that reality is deeper, broader, more mysterious than anything we see day to day. It suggests that what we call the universe may be only one page in an endless cosmic volume. And yet, even within this immense multiverse, our experience remains personal, specific, grounded in a single unfolding moment. It also forces us to rethink the nature of possibility. When you stand before a choice, it may not be that one path is taken and the others fade away. It may be that all paths unfold, each in its own branch. You experience only one, of course, but the others continue, carried forward by versions of you that are not you, and yet are, in some strange quantum sense. There is something both humbling and liberating in that. The universe becomes less a rigid sequence of events and more an ocean of possibilities in motion. A place where reality is not singular but plural, not confined but expanding continuously. And yet, for all its philosophical beauty, the many worlds view is difficult to test. We cannot access other branches. We cannot send messages between them. We cannot step outside our own slice of the wave function to peek at its sisters. At least, not with anything we know in this quiet span of 2025. The interpretation remains a powerful, haunting idea, one that sits at the edge of science, inviting us to wonder whether the universe is far larger than our senses can grasp. But whether or not the multiverse is real, the idea offers a lens through which to understand quantum mechanics with uncanny clarity. It reminds us that the quantum world is not merely small, it is layered, it is branching, it is suffused with potential that extends far beyond what we perceive. And perhaps the most mesmerizing question now is this: if reality can branch, if space can be shaped by entanglement, if possibility itself can blossom into universes, then what are these universes made of? What lies beneath them? What is the underlying structure of reality that allows such branching, such coherence, such richness of form? Well, that gentle question leads us toward the next revelation waiting for us, toward the idea that beneath particles, beneath forces, beneath even space itself, lies a deeper framework woven from fields that ripple through the vacuum, fields that give rise to everything we see. Let us drift softly toward that hidden foundation together. Well, you see, after drifting through the branching forests of the multiverse, where every quantum possibility unfurls into its own shimmering world, it becomes natural to wonder what lies beneath all these universes. What is the canvas on which they are painted? What is the deep machinery generating particles, shaping forces, guiding the growth of galaxies and the trembling of atoms? When we look closely, closer than particles, closer than waves, we discover that the universe is not built from things at all. It is built from fields, vibrations, continuous oceans of energy that stretch through all of space. And this is where our journey carries us next, toward a truth so subtle and yet so foundational that it reshapes our sense of emptiness itself. Imagine for a moment that space is not a void but a vast fabric, like an ocean without a surface. Everything that exists, particles, forces, even the energy that fills the cosmos, arises as ripples on this ocean. These ripples are what we call particles. A photon is not a bead of light, but a vibration in the electromagnetic field. An electron is not a tiny point darting around, but a disturbance in the electron field. Every type of particle corresponds to its own field, and those fields permeate all of space, everywhere, always. This is perhaps one of the most poetic ideas in physics. The universe is a symphony of fields, and particles are the notes. They arise when fields vibrate at particular frequencies. Matter is not a solid thing. It is a sustained ripple, and you, me, the stars overhead, we are all woven from these ripples stirring gently in the cosmic fabric. But what about emptiness itself? What about the quiet, dark spaces between stars? The void that seems to stretch endlessly across the night sky? Well, once we step into the realm of quantum fields, we realize that emptiness is anything but empty. The vacuum seethes with energy. Tiny fluctuations ripple through it continuously, even in the coldest, most silent regions of space. Fields cannot rest. They cannot sit at perfect zero. They jitter with quantum fluctuations, producing ephemeral particles that flicker into existence and vanish almost instantly. And that's the thing. These fluctuations are not hypothetical. They are measurable. They exert pressure. They influence how atoms behave. They bend the trajectories of particles. Even emptiness has structure, texture, a kind of restless undercurrent. The vacuum is alive in a way that defies our classical intuition. If you could somehow shrink yourself down to the smallest conceivable scale, drifting between the particles that make up your body, you would not find emptiness. You would find a storm, a sea of quantum fields vibrating and fluctuating, and perhaps in a quiet way that makes the universe feel strangely intimate. The very space around you is alive with motion. Stillness is an illusion. When we talk about particles emerging from fields, it might help to imagine waves rising on the surface of a deep ocean. The waves are real, but they are not separate from the water. The ocean gives them their shape, their motion, their energy. In the same way, the quantum fields are the deeper reality. Particles are just the waves they create. This helps us understand something else. Fields stretch across the entire cosmos. They do not end at borders or fade into nothingness. They are continuous. They fill all space. The electron field that produces the electrons in your body is the same field that produces electrons on the other side of the universe. There is only one electron field, one photon field, one quark field. And every particle we see is an excitation of these fields. In a sense, the universe is one interconnected medium, expressing itself through vibrations. And perhaps this is why the vacuum's energy density matters so deeply. These ever-present fluctuations influence the expansion of the universe. They contribute to the mysterious dark energy that stretches space apart. They shape the structure of matter in the early cosmos. Even the Big Bang itself may have arisen from a quantum fluctuation in a primordial field, a moment when the calm of the vacuum surged into a burst of expansion. It is almost poetic to think that the universe could be the result of a ripple in nothingness, except that nothingness, in the quantum sense, is rich with potential. The vacuum is a wellspring of creation. It can give rise to real particles under extreme conditions. In high-energy events, such as near black holes or in particle accelerators here on Earth, the vacuum can be stirred so violently that virtual particles become real. They emerge from the fields like sparks thrown from a fire. But even in calmer settings, vacuum fluctuations play a role. They shift the energy levels of electrons in atoms. They contribute to the Casimir effect, where two metal plates placed close together feel a mysterious attraction due to the behavior of vacuum fields between them. They even shape the geometry of space-time. The vacuum is a participant in the evolution of the universe, not a silent backdrop. One of the most fascinating ideas to emerge from modern physics is that fields might be the true building blocks of reality. Matter, energy, space, even time may all arise from their interactions and excitations. When we speak of particles, we are speaking of localized excitations of fields. When we speak of forces, we are speaking of interactions between these excitations. When we speak of space, we are speaking of the stage on which fields exist. But some physicists believe space itself may emerge from the structure of entangled fields. Perhaps then the vacuum is not merely a void, but a deeply woven fabric of potential from which everything else arises. The universe becomes less like a collection of objects and more like a tapestry of interconnected vibrations, a grand harmony, a cosmic wave. And if fields extend everywhere, if the vacuum itself carries structure and energy, then the boundaries between something and nothing begin to blur. It becomes difficult to say where matter begins and space ends. In quantum field theory, space is not passive. It does not merely host the universe. It participates in it. It creates, it influences, it responds. This brings us back softly to the idea of entanglement we encountered earlier. If fields stretch across space, then particles born from the same fields share deep connections. Entanglement becomes natural. The vacuum itself becomes a web of relationships. Space is not an empty container, but a network of links, of correlations, of fluctuations. The universe is relational at its core. And once you allow that thought to take root, everything begins to feel a little different. The emptiness between galaxies feels less cold. The space inside an atom feels less hollow. The universe becomes a dynamic field of activity, rather than a stage filled with isolated actors. Perhaps this is why the idea of quantum fields resonates so deeply with modern cosmology. The early universe was a cauldron of field interactions. Fields collided, vibrated, and inflated. Ripples in fields became the seeds of galaxies. Quantum fluctuations at the dawn of time became the structure of the cosmic web we see today. Even the accelerating expansion of the universe may be driven by vacuum energy, by the restless hum of quantum fields that refuse to lie still. When we imagine the universe in this way, the Big Bang is not merely an explosion, but a transformation, a phase change, a moment when fields shifted into a new configuration, releasing energy, matter, and space itself. Time began not in emptiness, but in a roiling sea of quantum activity. And that realization nudges us toward another profound question. If fields underpin everything, if the vacuum is alive with vibration, then what does this say about time? Is time an independent river flowing past field excitations? Or is it, too, something woven from the behavior of fields? Could the strange flexibility of time in quantum experiments, the way events can seem to blur forward and backward, be rooted in the fluidity of underlying fields? Well, that question, drifting like a spark from the vacuum itself, leads us into the next chapter of our journey, a chapter where time loses its steady march and becomes something far more mysterious, something that bends and loops and sometimes seems to flow both ways. Let us move softly toward that strange horizon together. Well, you see, once we've begun to sense the restless life of the vacuum, that trembling sea of fields where nothingness is never truly still, another question starts to bloom. Quietly, almost shyly, at the edge of our understanding. If space is not empty, if fields hum beneath every breath of reality, then what about time? Does it flow gently over this ocean like wind over water? Or is time itself another kind of vibration, another field, another subtle rhythm shaped by quantum rules? And the more we look, the more we realize that time, too, becomes strange in the quantum world. It bends, it blurs, it misbehaves. It refuses to march forward in the steady, predictable way our daily lives depend on. We like to imagine time as a river that flows from the past to the future, carrying us along with it. That picture feels comforting, doesn't it? Ordered, familiar. But in the quantum realm, the river looks less like a steady current and more like a shimmering pool of possibilities. Events do not line up neatly in a single direction. Instead, they can blur. They can rearrange. They can even seem to influence one another in ways that violate our common sense. To begin with, time does not flow continuously at the smallest scales. It is not a smooth thread. When quantum systems are isolated from measurement, time becomes elastic. Events stretch or compress. Processes unfold in ways that defy classical order. In a world where particles exist in superpositions, where they occupy many states at once, time itself behaves in a similar way, allowing multiple sequences of events to coexist until observation forces a single ordering to emerge. It's almost as if time is a landscape rather than a line. When you stand far away, it looks like a simple horizon. But the closer you approach, the more hills and valleys appear, paths that split or merge, routes that loop back on themselves. Time, in this sense, becomes a terrain of possibilities. One of the strangest discoveries is that particles can appear to exist before they are created. It sounds impossible, I know, and yet experiments in quantum optics have shown correlations between events that seem to reach backward in time. The present, in delicate quantum experiments, can influence how we interpret the past. The measurement you choose today can determine how a particle behaved yesterday, or at least how the mathematics describes it. Reality becomes a negotiation between past and present, shaped by the entire context of measurement. And that's the thing. The quantum world does not obey the classical arrow of time. In classical physics, causes led to effects. The past influences the future, never the other way around. But quantum mechanics does not enforce this rule. Instead, it allows for something more subtle. Causes and effects can blur. The distinction between before and after can become ambiguous. Some experiments show that the order of events, whether A happens before B or B happens before A, cannot be defined until the measurement forces the system to commit. Imagine two friends walking a path through fog. From afar, it seems clear who leads and who follows. But as you approach, the fog thickens, and suddenly you cannot tell who is ahead. The sequence dissolves. Only when you shine a light, your measurement, does the fog part, and one path emerges as the story you experience. Quantum causal order works much the same. Without measurement, events can exist in superposed orderings, neither definitively before nor after. Time loses its rigidity. It becomes flexible, contingent, responsive to the structure of interactions. This flexibility of time is most evident in quantum tunneling, where a particle slips through a barrier without crossing the space in between in any classical sense. When scientists try to measure how long tunneling takes, the answer becomes slippery. Some measurements suggest the particle tunnels faster than light. Some suggest it takes no time at all. Others say the question itself is ill-defined. Time in the quantum realm is not a stopwatch ticking steadily. It is a quality that emerges only when we observe it, just like position, momentum, and other properties. And it gets stranger still. When quantum systems are not observed, the temporal rules can relax so much that a particle can effectively interact with versions of itself in the past. The mathematics suggests loops, self-influences, feedback across time. Not time travel in any cinematic sense, but a kind of temporal ambiguity that allows quantum states to interfere across moments. Perhaps this is why the universe does not enforce an absolute causal order at small scales. If you zoom down to the realm of particles, causality becomes a matter of probability rather than certainty. The universe does not decree that event A must precede event B. Instead, it allows for a cloud of possible orderings, which only collapses when interactions force a decision. And this raises a profound question. Does time exist independently of events? Or is it something that emerges when systems interact, when measurements occur, when branches of the multiverse decohere? Many physicists suspect that time is not fundamental but emergent, that it arises from correlations between quantum systems. In this view, if nothing changed, if nothing interacted, if nothing measured anything else, time would have no meaning. It is a relational concept, born from the dance of fields and particles. When we look at the early universe, time seems to behave even more strangely. In the moments before the Big Bang expanded into the universe we know, the quantum fluctuations of primordial fields blurred the meaning of before and after. The birth of the universe may have been less an explosion in time and more a transition into time. The arrow of time, the direction we feel so deeply forward, may have emerged only after entropy began to rise, only after quantum systems decohered and formed classical structures. And once you let that sink in, it becomes clear that time's direction, its arrow, is not absolute. At the quantum level, the equations do not demand a preferred direction. They run equally well forward or backward. Time becomes a thin veil draped over deeper laws that do not themselves care which way the arrow points. But we experience time as flowing. Why? The leading idea is that the arrow of time emerges from entanglement. As systems entangle with their surroundings, their states become irreversibly mixed. This spreading of information, this growth of entropy, gives rise to the experience of one-directional time. In other words, time flows because information spreads, because correlations deepen, because the universe keeps getting more entangled, and yet beneath that apparent flow lies a world where time can flex and bend, where events can lose their ordering, where the present can influence the past in peculiar, non-classical ways. You know, when you sit with these ideas long enough, time starts to feel less like a river and more like a tapestry. At the surface, it looks like a simple line, but beneath, countless threads intertwine, warp, and cross. The weave gives the illusion of direction. The deeper fabric does not. And perhaps that is what makes the quantum perspective so humbling. It loosens our grip on time. It whispers that our experience is not the full story, that beneath our everyday feelings of past, present, and future lies a more fluid, more mysterious structure. One shaped by fields, by entanglement, by the collapse or branching of possibilities. This naturally leads to an even more provocative question. If time is not fundamental, if it bends and blurs in the quantum world, then what does this mean for the technologies we build? For the devices that rely on quantum precision? For the instruments that must navigate the dance between relativity and quantum mechanics? Well, that gentle question begins to pull us toward the next horizon in our journey, toward a place where theory meets invention, where quantum strangeness becomes a practical tool, a place where fields, uncertainty, and the soft shimmer of time feed directly into the technology of our modern world. Let us walk softly into that unfolding landscape together. Well, you see, after we've wandered through that shifting landscape where time bends and blurs, where the arrow of causality softens and the quantum world whispers that even before and after may be matters of perspective rather than absolutes, we eventually find ourselves standing at a threshold. And perhaps it is here, in this quiet place between mystery and application, that the universe leans in and says, all of this strangeness, you can use it. And that realization is both thrilling and humbling, because quantum physics is not merely a theory carved into blackboards. It is woven into the machinery of our modern world. It breathes inside our hospitals, our phones, our satellites. It shapes our civilization in ways so seamless, we often forget the magic beneath the metal. And so, let us drift gently into this idea, that the deepest strangeness of the universe has become a toolbox, quietly powering daily life. Imagine for a moment the soft hum of a hospital corridor. Someone you love lies inside an MRI scanner. The machine produces detailed images of their body without slicing, without touching, without harming. And the astonishing thing is that it does so by borrowing the tricks of quantum mechanics. MRI works because atomic nuclei, especially hydrogen in the water of our bodies, possess quantum spins. These spins behave like tiny magnets, flipping and aligning in response to magnetic fields. The signals they emit as they relax are quantum signatures, delicate whispers from the atomic world. And we rebuild those whispers into images, maps of tissue, blood flow, neural activity. It is deeply human technology powered by quantum effects. And that's the thing. Quantum mechanics allows us to see inside the body without ever opening it. It turns the invisible into something visible, something healing. Now consider the laser, that sharp, precise beam of light cutting through surgery, or carrying your voice across oceans. A laser is not just bright light, it is quantum light. It arises from stimulated emission, a process where one photon triggers another and another, all in perfect unison. They march together, like soldiers in step, forming a coherent beam that does not scatter or fade the way ordinary light does. Every supermarket scanner, every fiber optic cable, every DVD player, every piece of modern communication owes its existence to that quantum effect. Perhaps the most poetic part is this: the laser works because atoms do not emit light whenever they please. They emit in quantized steps, in specific transitions, triggered by other photons. The quantum world gives us order, coherence, precision. And then there is GPS, the invisible companion of modern life. The quiet voice in your pocket that tells you where you are in the world. You might think GPS is simply satellites and mathematics, but beneath its calm instructions lies the marriage of quantum mechanics and Einstein's relativity. The clocks inside GPS satellites are atomic clocks, among the most precise timekeepers humanity has ever created. They rely on quantum transitions inside atoms to mark time with astonishing accuracy. Without that precision, without quantum mechanics, the position readings on your phone would drift by kilometers in just a day. And of course, relativity tells us that time flows differently for moving satellites than for us on Earth. Those corrections are essential too. GPS works because the universe allows us to combine quantum rules of small scales with relativistic rules of large scales. Humanity navigates the globe by riding on the shoulders of two of nature's deepest theories. If we drift a little further into the circuitry of modern life, we find that every computer chip, every transistor, every integrated circuit also arises from quantum principles. The behavior of electrons inside semiconductors depends on quantum energy bands, on tunneling, on the strange ways electrons spread like waves inside crystal lattices. Without quantum mechanics, the digital revolution, the internet, the world we inhabit today, none of it would exist. You see, the transistor is not a classical switch. It is a quantum barrier. Electrons tunnel, drift, and gather in ways determined by discrete energy states. Every message you send, every video you watch, every line of code you write, depends on electrons behaving in ways that only quantum physics can explain. And perhaps that is where we realize something beautiful. The biggest transformations in human civilization have arisen from our ability to harness the smallest of scales. Atomic clocks, too, push the boundary of precision even further. In these clocks, atoms vibrate at frequencies so stable that we can measure time to incredible accuracy. They do not drift for millions of years. They define the second. They anchor global communication networks. They synchronize scientific instruments across continents. And they depend entirely on quantum transitions, on electrons absorbing and releasing energy in perfectly quantized steps. In this way, the passage of time for our entire world is a quantum rhythm. But the true frontier of quantum technology, the one that tingles with the same uncertainty and promise that early electricity once held, is quantum communication. The idea that entangled particles can create networks that are fundamentally secure, not secure by complexity, not by encryption that might eventually be cracked, but secure by the laws of physics themselves. In quantum communication, if anyone tries to eavesdrop on the link between two parties, the entanglement shatters. The intrusion reveals itself instantly. The universe itself becomes the guardian of information. No classical hacker can breach it. No computational power can break it. It is security written into the fabric of nature. And while this might sound futuristic, quantum networks are already being built. Across research labs, across cities, even between Earth and satellites. Quietly, without fanfare, humanity is laying the first threads of a quantum internet, a network that will one day carry information not as bits but as qubits, delicate, shimmering, entangled states that cannot be copied, cannot be intercepted, cannot be stolen. And if we lift our eyes a little further ahead, we see quantum computers emerging like strange new creatures, machines that do not think in ones and zeros but in superpositions, machines that can explore many possibilities at once, machines that, if stabilized and scaled, could solve problems so vast that classical computers would take longer than the age of the universe to complete them. These computers are fragile, almost impossibly delicate. The slightest noise can collapse their quantum states. And yet, even with these challenges, prototype quantum machines already exist. They are early steps, shaky and shimmering, into a computational future that feels alien to us today. The logic is different. The flow of information is different. The entire architecture of reasoning inside a quantum machine bends to the laws of superposition and entanglement. And, the thought that humanity is building such machines that whisper in the language of the universe itself, is astonishing. We are learning to compute using nature's deepest truth, and yet the quantum technologies of today barely scratch the surface of what may come. If we can stabilize qubits, build error correction systems, tap into advanced entanglement networks, the entire landscape of human knowledge may transform. Quantum chemistry could reveal new medicines. Quantum materials could reshape energy. Quantum algorithms could solve optimization problems we cannot even articulate fully. The future, like a wave function, spreads before us in many possibilities. But as powerful as these tools are, they all point back to a deeper question. If quantum rules shape everything from medical scanners to navigation satellites, from lasers to computers, from clocks to communication networks, then what about life itself? After all, biology operates on molecules, on atoms, on electrons. Could quantum mechanics whisper inside living systems too? Could it guide the way birds navigate? Could it influence photosynthesis? Could it play a role in the deepest processes of the brain? Well, that gentle question, rising from the edge of physics and the threshold of biology, invites us into the next landscape of our journey. A place where life and quantum mechanics meet. A place where the strange rules of the microscopic world shape something warm, something breathing, something conscious. Let us step softly toward that mystery together. Well, you see, once we begin to understand how quantum mechanics breathes inside our technologies, whispering through MRI magnets, humming through lasers and transistors, bending time inside atomic clocks, a softer and even more intimate question begins to emerge. It comes not from machines or satellites, but from something far closer, far warmer. It comes from life itself. And, perhaps you've felt this question lingering already. If the universe at its deepest level runs on quantum rules, then why would biology be exempt? Why would living systems built from atoms and electrons, sustained by sunlight and chemistry, not also feel the trembling, probabilistic, wave-like logic of the quantum world? We often picture biology as classical, warm, wet, messy. A world where molecules jostle, proteins fold, nerves fire, hearts beat. But beneath all that motion lies the quantum realm, subtle yet omnipresent. And the more carefully scientists look, the more hints they find, places where quantum effects seem not only present, but essential. Life, it turns out, may not merely tolerate quantum mechanics. It may depend on it. Perhaps the clearest example lies in a leaf. You've seen sunlight filtering through trees, warm and golden, scattering across your skin. But inside each leaf, inside each tiny chloroplast, a quantum ballet unfolds, something so delicate and efficient that engineers are still struggling to replicate it. Photosynthesis, the process by which plants turn sunlight into chemical energy. Classical models once assumed that energy hopped randomly, molecule by molecule, stumbling through the photosynthetic machinery until it found its destination. But experiments show something far stranger. The energy does not stumble. It glides. It explores all possible routes simultaneously, like a wave moving through a maze of mirrors. In other words, the energy harnessed from sunlight exists in superposition, sampling paths in parallel until the most efficient route emerges. It's astonishing, really. Plants, in their quiet stillness, perform a kind of natural quantum computation every time sunlight touches them. They move energy with near perfect efficiency because they use quantum coherence, not unlike a qubit evaluating multiple possibilities at once. Nature discovered quantum optimization long before humanity understood what it even meant. And that's the thing. Life is not merely chemistry, it is choreography. It uses quantum effects not as rare accidents, but as tools. Consider the birds. Each year, migratory species cross continents with breathtaking precision, navigating thousands of kilometers using a sense we still struggle to comprehend fully. They seem to see Earth's magnetic field. And strangely enough, the mechanism that enables this may rely on quantum entanglement. Inside certain proteins in their retinas, chemical reactions generate pairs of electrons whose spins are entangled. These entangled states are exquisitely sensitive to magnetic fields. As the bird turns, the entangled spins evolve differently depending on orientation, creating a visual pattern, a shifting quantum compass that overlays the world. Imagine that for a moment. A robin perched on a branch at dusk, tilting its head just slightly, unconsciously reading the quantum entanglement unfolding inside proteins in its eyes. The bird navigates by quantum rules, guided by delicate correlations that persist in the warm, noisy environment of a living body. It is a kind of quiet miracle. And once you start to notice these examples, more begin to appear. Enzymes, those molecular machines that catalyze the reactions sustaining life, often rely on quantum tunneling. They don't wait for particles to climb energy barriers. Instead, they allow protons or electrons to tunnel through those barriers, drastically speeding up biochemical processes. Without quantum tunneling, many essential reactions in the body would be far too slow to support life. DNA, too, may feel the touch of quantum mechanics. Some theories suggest that quantum tunneling within base pairs can influence mutation rates, that quantum effects may subtly shape the evolution of life. It's not that DNA becomes mystical, it remains a molecule, but the rules that govern its motion, stability, and interactions trace back to the quantum realm. And then there is consciousness, that quiet, persistent mystery. Some scientists have proposed that quantum processes might contribute to how the brain integrates information or how neural networks achieve coherence. These ideas remain speculative, of course. The brain is warm, wet, and noisy, conditions that tend to destroy delicate quantum states. But the possibility alone raises a deeper question. Could thought itself, in some faint and indirect way, be brushing against the quantum world? Even without leaping into speculation, one thing becomes clear. Biology is not separate from quantum physics. Life is built from atoms, and atoms are quantum. But more intriguingly, life seems to have learned, through billions of years of evolution, to use quantum rules strategically. Not everywhere, not all the time, but at certain critical points, navigation, energy transfer, enzymatic action, it leans on the quantum world to achieve efficiency and sensitivity no classical mechanism could provide. When you sit with that idea, it reshapes something inside you. Life is not only adapted to the universe, it is adapted to the quantum nature of the universe. The roots of trees, the wings of birds, the chemistry of cells, all of them quietly reflect the rules we've been exploring in these chapters. Superposition in leaves, entanglement in eyes, tunneling in enzymes, coherence in molecules. Life is not an exception to physics. It is one of physics' most beautiful expressions. And perhaps that realization nudges us towards something even more profound. If biology uses quantum effects, then maybe our own sense of reality, our intuition, our perceptions, our sense of causality, might be shaped in part by how quantum processes scale upward into the world we inhabit. Maybe some aspects of consciousness or memory emerge not from classical computations, but from quantum interactions woven into neural biochemistry. We don't know yet. The questions here remain open, shimmering like superpositions unmeasured. But they are among the most exciting frontiers in science, because they ask not merely what the universe is made of, but what we are made of. They ask whether the strangeness we see in the quantum world is not alien but familiar, written into the cells that make us, the breath we draw, the life we live. And if quantum mechanics can help plants harvest sunlight, guide birds across the skies, accelerate the reactions inside our bodies, and perhaps even whisper through the forests of our neurons, then what else might it explain? What other mysteries of existence might trace their roots to the trembling fields beneath reality? This question, soft, subtle, almost philosophical, invites us toward the next horizon. A horizon where quantum strangeness becomes not merely useful, not merely biological, but foundational. Because if life embraces the quantum, then perhaps the most counterintuitive truths of quantum mechanics touch not only science, but our deepest philosophies, our sense of certainty, of identity, of reality itself. And so, with this thought lingering gently in our minds, let us drift forward toward the most paradoxical, mind-bending, intuition-shattering corner of the quantum world. A place where the rules of logic falter, where reality becomes probability, where existence becomes vibration, where the universe reveals not just its mechanisms but its mysteries. Let us step softly into that space together,